Good evening, Doctor. This is Kamandatha from Group SWML26, and I'll be presenting about our project which is concerned with Babesia disease detection in ticks. In animals, which is a tick-borne disease. This is my table of contents that I'm going to follow the introduction. These are the two model textures that I included in my project: AfficientNet before and then MobileNet V2. I'll explain how the model learns, how it works, the optimization, normalization, and the results that will be that took from the simulations that I made using the evaluation method, the evaluation file. And then also explain the learning rate, conclusion, and the limitations. So in this project, for babesiosis disease detection in animals, I will basically have four classes of datasets, and these include the Babesia, Plasmodium, the rebel cells, and then the leukocyte. As we have our data, babesiosis class is composed of the positive images, which are diagonized all unhealthy, consisting of babesiosis, one of our major concern. And then you also have the plasmodium images. These are negative images, but we doctors or the veterinary doctors usually have a difficulty in differentiating babesiosis disease and then plasmodium, since both of them have the same ring shape, which brings a lot of confusion, especially when they're doing the research, so that to determine which one is which, and this takes more time. So we also have it and shall learn its patterns so that we can when doing when someone is using a model, is using a model, we can easily distinguish between whether it is babesiosis or plasmodium, and then also to distinguish whether between it is healthy or unhealthy. So these are the model architectures that we are going to use: efficient net before, and then the mobile net v2. Efficient net, I will start with explaining the network architecture for efficient net before. The core idea for it, EfficientNet introduces EfficientNet introduces the compound scaling, which means instead of randomly increasing the layers or filters, it focuses on the scales, on the depth, the width, and then image resolution together in a balanced way. Unlike ResNet 18, which uses ResNet networks or the skip connection to the HC training or the HC model learning. So this provides a better performance compared to the traditional scaling methods. EfficientNet before is a larger version compared to B0, which we had in our first models. For it uses around 19.0 million parameters, whereas EfficientNet B0 was using it had like 5.3 parameters, and this gives B4 higher accuracy for complex tasks like the medical image analysis. We have the key building blocks. Initially, we have the stem, which acts as the first layer that extracts the basic features like the edges, textures, using a standard configuration. It is composed of 48 filters, a kernel size of 3 by 3, and then two sprites. Then it is then followed by the body, which is made up of multiple MB conf blocks, which are efficient configuration in its original form. Mobile net, remember MB conf stands for mobile inverted bottleneck configuration blocks. So efficient net before is composed of 7 stages, and each stage is composed of these MB configuration blocks. So inside the body, we have the squeezing and excitation blocks, which helps the network to focus on the most important features. That is, that term as channel attention, whereby we only focus on the features that we want our model to be used to. For example, if you're focusing about the edginess of the images, the resolution of the images, so look for some of the important features that our model should basically look at while training it. As you go deeper, the number of filters increases from 48 to 448, allowing the model to learn more complex patterns compared to B notes. And compared to note, B4 has more layers, meaning it has a deeper learning extraction compared to other models. So this from there we shall have our activation and then also the final stages. The model uses the switch activation, which improves the gradient flow and then the overall performance compared to ReLU. From there, you have our global average pooling, which reduces the feature maps into a single vector, making the model more efficient and then reduce overfitting. Number for which basically looks at converting the map. Sorry, it will basically look the average pooling. Basically, it focuses on converting the feature, on extracting and converting the feature maps or the feature maps to vectors. And finally, we shall have our fully connected layer with softmax, which produces the class predictions. For example, we may have different Babelsia species, and it will be giving the probabilities for each class. For example, if someone uploads an image, we shall have our Babelsia percentage, and it will be the role of the fully connected layer and the softmax to display those results to the user so that they can understand the percentage of each in the cell that will be provided. Efficient NetBeam improves actually by scaling the network in a balanced way. It uses the efficient MBV conv blocks with the attention mechanism and ends up with pulling and then classifying the prediction. That's what I can give about the architecture. And then from there, want to go to the next layer. Sorry. Then I will proceed with my Lucid chart, which explains the architecture, how the architecture flows. Initially, of the image input, which takes in dimensions of 224 by 224 of the images. Then from there, we shall have our stem convolution, which extracts the lower level features such as the edges and then the textures. We have the two strides, which reduce the image size while increasing the feature depth. Then from there, we shall go to our convolution blocks, our mobile MB conv blocks, which do the feature extraction and diving deeper into the image to understand it clearly, the cells, the parasites that are found in the cell that has been provided. So this is how I can explain these conv blocks. The core of the model is made up of many conv blocks, MB conv blocks. These are efficient convolution layers that reduce the computation while maintaining the accuracy of our model. As we move forward, we have different filters, and each layer is made up of different feature. Each layer is made up of different filters. For example, layer 1 has 24 filters, layer 2 is composed of 30 filters, and then also the other layers up to the final layer, which is composed of 272 filters. This allows the network to learn more complex patterns. This allows the going to learn more complex patterns. By the time we reach the final layer, the one that is composed of 270 filters, the model will be able to distinguish that this cell is composed of Babesia, or it is healthy or unhealthy. That's giving a final output or result to our veterinary doctor who will be analyzing the image. Then from there we have our maybe in the before reaching the final layer, we have a progression throughout these layers. Initially we shall have the early stages. For example, detecting the simple patterns like the edges, the shapes, the size of our image, and then you shall have the middle layers, which you concentrate on we be concerned with detecting the structures, for example cells and then the parasites. And then the deeper layers, for example like the sixth and the seventh, for them they will be concentrated on understanding the complex and then the biological features within those cells. Then from there we shall go to the global average pooling. This reduces the feature maps into a single vector, which helps us to reduce overfitting. Then you have our second model architecture is the mobile net V2 architecture. For it, it has its core idea. It uses the dipwise separable convolutions. It has the inverted residual bottleneck blocks, which help us to analyze the image since it passes through different blocks. The bottleneck blocks analyze the edges, dive deeper to understand the cells, the parasites, and then also to determine the structure of the cells, the rings, how they are structured. That gives a better insight of the model to learn how the pattern has flow in our cells. So we have our key blocks, the conv 3 by 3, which is composed of 32 filters and then two sprays. And we have the bottleneck block, which is composed of 1 by 1 expand and then 3 by 3 dipwise and then 1 by 1 of the project. Then we have different stages. I have stage 1 up to stage 1 up to stage 320. Remember, in each stage we are analyzing the image, the patterns, simple the simple things like the edges, the edge, image size, resolution. Then as we go further, we are analyzing the deeper and also understanding the deeper structures in our cells that we can easily distinguish whether it is healthy or unhealthy. Then you have the final layers, where we shall have also the global veg pooling, the dense and then the soft marks. Remember, the dense acts as the fully connected layer, which produces the output of the classes after the global average pooling. From there, we shall go to our mobile net V2 diagram. It's a LCD chart, and then shall also explain how the flows from the initial step and then the final step. Initially, we have the input and the initial conversion. And the model starts with an image input as the initial state. Then the first conversion layer extracts the basic features such as the edges, reduce the image size using the two strides. Then you have the first bottleneck, which is composed of the 16 filters. This is the simplest block with minimal expansion. It begins feature learning while keeping the computation somehow low. Then you have the bottleneck blocks for different filters such as from 32 to 64. And these blocks expand feature maps, apply deploys configuration, and then decompresses them. This helps to capture more complex features while keeping the efficiency. Then you have our more as you go to deeper layers, we have the deeper layer, bottleneck layers, which have more filters. For example, 96 to 130, 160, and then 1020 filters. As you know, as the depth increases, the model lines more detailed patterns. And these layers capture more complex structures such as the cells, the parasites. Then you have the key concepts that are you can summarize in our layers. Each bottleneck layer follows the following things: expansion, the deepwise configuration, and then also analyzing the project. And they use the remember mobile network uses mobile mobile net V2 uses the inverted residual connections for efficiency and then also better training. Then from there we shall have our global veg pooling, which converts the feature maps into a single vector. This reduces the model size and also prevents overfitting. Then you have the fully connected layer that maps the extraordinary features into their final output classes. In the softmax output, it produces the probabilities for each class, the Babesia, leukocyte, plasmodia, and then the red blood cells. So I can summarize this architecture by saying that the mobile VNet processes the images through efficient bottleneck layers or blocks and then outputs the class probabilities using a lightweight architecture as described in the slides. Then my next presentation will be on how the model lines. First of all, initially we have our input data. The model uses the microscopy images of blood cells as our input. These images are labeled into four classes: the Babesia, leukocyte, plasmodia, and then also the normal red blood cells. This allows the model to learn how to distinguish between the infected and then the healthy ones. Since we have grouped our data sets, then from there we shall have our data argumentation. This will help us to improve how our model analyzes these images. Under the data argumentation, we shall start with random sized crop, which standardizes our images into a ratio of 2 by 224 by 224. Then we have the flipping, the horizontal, and then the vertical. This helps our model to learn the orientation invariant features. For example, if the image was taken in a vertical direction, our model will be able to analyze that position. If it was the horizontal, the same way. If it was any of the two, the model can analyze it well without getting any confusion. Then you have the random rotation for angles greater than 30 or less than 30. This will simulate the real-world variations in microscope positioning. For example, our microscope can be placed in different directions, in different angles. So no matter the angle, our model should be trained to analyze every positioning of our microscope. The images how they be taken either from any angle. Our model has to be able to analyze every angle that our images have been taken. Then you have the color jitter, and this one adjusts the brightness, the contrast, which will help us to handle the strain differences uh, in the images. No matter the color that was the image was taken, our model has to be able to analyze to adjust the brightness and then the contrast. And this will help us to reduce the overfitting and then it will also improve robustness. So we have some of the extra features such as our models that you're going to train. Remember, we use in the deep learning models we are using efficient B4 and then MobileNet V2 as our feature extractors. So these models automatically learn important patterns from these images that we provided. This is where the model learns. One of the most important things, the model will be able to detect the edges and the textures, the cell shapes, and also the structures. And then also in the final layer, to define the parasite specific patterns, which are critical for classification, especially in our project. The parasite specific patterns help us to understand uh, whether the image is diagnosed with Babesia or not. The summary that I can give on this is that our model processes the augmented D. Because remember you're using the blood smear images, and they use our deep CNNs to learn the features from these simple edges, the complex patterns, and then so that we can get the better choice in our model when training our model. Then more explanation on how the model learns. We have the prediction. The model outputs probabilities for each of the four classes. These probabilities indicate how confident our model is for each class. So the class with the highest probability is selected as the final prediction. Then you can also talk about the losses. We use the cross entropy loss, which measures how far our predicted model probabilities are from the true labels. For example, if the cross entropy loss is low, that means our model is somehow near to our expected outputs. And if the percentage of the cross entropy is high, that means our model is still far from what we expect from it. That means it's giving us an abnormal value or a wrong value. Since the data sets may be imbalanced, we can apply the class weight in order to minimize this. This ensures that the minority classes, for example, in our case, the infected cells were somehow few, they are not ignored during the training. So this is how we optimize our model. So we have the backpropagation, which is used to compute gradients of the losses. These gradients show how the model weights should change to reduce errors. We use Adam W optimizer with a learning rate of 0.001 to update our weight efficiently. Additionally, for normalization, we use Masenko strain normalization, which is applied to reduce the variations in training across the different images, thus improving our model or maintaining our model consistent. So we can improve our model via running multiple epochs. Remember, whenever we run our epoch, our model is going through our dataset, analyze, identifying the different pattern structures in it. So the more we do more epochs, is the more how our model lines. So after each epoch, we monitor the validation attributes to check the performance of the unseen data. For example, when you're doing the evaluation, we are basically evaluating our data that was not used in training. So whenever we do the validation, we need to get the validation attributes to know how accurate our model is with unseen data, the one that we need to use it for training. So the best model is then saved to avoid overfitting and also to ensure optimal results. So this is how our model works. Initially, we have our input which is the images, and these images are taken from the game's stained blood smear images. So these images are resized again while training your model in a ratio of 224 by 224 pixels with RGB channels, and this ensures that we have this compatibility with our scene models, because for them they use, according to how we set it, it is considered images that are being resized in the width of 200, in the dimensions of 224 by 224 pixels. So we have our core architecture, which we are using two models, EfficientNet V4 and then MobileNet V2. EfficientNet V4 uses compound scaling, a balanced depth, and then a resolution for better accuracy. It also uses the the conv blocks, which are efficient and powerful for the future extractions. So our MobileNet V2 focuses on the efficiency using the depth-wise separable convolutions and then inverted residual bottleneck blocks, making it lightweight and fast. This is how our prediction process goes. The first step is that the image is passed through the network as an input. Then the convolution layers extract the feature progressively from simple edges to complex shapes, and then parasite patterns as we move from one layer to another layer. Then you have the pooling layer, which reduces the spatial dimensions, making computation more efficient. Then you have the fully connected layer, which uses the features obtained from the average pooling so that we can make predictions. Then finally we have the softmax function, which converts the outputs into probabilities for each class. Our output consists of the model that has been selected with the highest probability during the final prediction. It also provides a confidence score for transparency. For example, if a model predicts Babelsia with a 92% confidence, then it is compared to the lower probabilities for other classes. So it is difficult to have the same percentages. One of the classes has to have a higher percentage that we can easily distinguish between the healthy and then the unhealthy. Then this is how I can explain. These are some of the output results for the FisherNet before. Initially, we have the conversion matrix, which shows our model performance for each class. The diagonal values represent the correct predictions, while the off-diagonal values indicate the missing classifications. I'll start with the leukocyte. Leukocyte model performs perfectly since we have 132 image correct predictions, implying there was no error since we had only 138 images that we used for leukocyte, and they all gave us the positive value. Then you have the red blood cells, which also performs well since it has 855 correct predictions. Though there were some inconsistencies that happened. Remember, the images were 889, but since you have the highest value, implying that there was a better performance. Then you have Babesia itself. It has a stronger performance, but a few of the samples are confused with other classes. Then also plasmodia is well detected with only minor confusion with the red blood cells, as we have, as you can see for plasmodium, we have two of them are confused with the red blood cells, and thus coming to our overall prediction on the diagonal, indicating our model has high accuracy and reliability. Then we have our precision and the recall and the F1 scores. And these metrics give a deeper evaluation of the model performance for each class. The precision makes how many predicted positives are actually correct. The recall measures how many actual positives are correctly identified. The F1 score helps us to identify the imbalances between precision and then also recall. Leukocytes actually they achieve the nearest perfect scores across all the metrics, showing an excellent performance. And then the red blood cells also give a higher precision and strong F1 scores, indicating that there is reliable classification in our output. Then Plasmodium has a high recall, meaning most of the true cases are detected, though precision is slightly slow. Then for Babesia, it has the lowest precision, suggesting some false positives, but recall remains high. Then a final the overall that you can give up, the overall comment that you can give on our models is that we have a strong and balanced performance across all of the classes, with only minor improvements needed for Babesia classification. Then you have our test set. For example, this is shown in our pie chart, which is displaying the the class distribution in our test set. We can observe the red by cells who dominate the data set, making it up to 72% of all the samples, implying that our model will be fed well on the norm of the healthy class on the healthy cells, and it is easier for it to understand to get normalized to the healthy cells, so that it does not make any mistake while predicting. Then the remaining classes, Babesia, leukocyte, and Plasmodia, have a significant few samples, which indicates some class imbalance problem that is minimized by our optimizer Adam W. Such imbalances can bias the model towards predicting the majority, so we minimize it using it. I will explain it later, but remember I talked about it. Then these are the output results for our mobile VNet, some as explained. Then also the class imbalance is also displayed. This is how I can describe our learning rate. The learning rate scheduler monitors the validation accuracy during training. If there is no improvement for the three consecutive epochs, the learning rate is reduced by halfway. And this helps our model slow down learning as it is approaching the optimal solution. As a result, the model can fine tune our weights more precisely and then avoids overshooting to the best point. Then we have the regulation techniques. To improve overfitting, several regulation methods are applied. For example, we have a dropout of 0.4, which randomly disables 40% of our neurons during the training, forcing our model to learn more robust features. We have data augmentation, whereby we have the rotation, flipping, color jitter, which increases the dataset diversity and also improve generalization. We have the weight decay in Adam W, which keeps weight small, leading to smoother and more stable learning. We have the early stopping and best model saving. And the model is saved only when validation accuracy improves. If the accuracy is consistent, the learning is stopped or it is done halfway. So that will ensure that only keep the best version. This ensures that the model we do this to ensure that the final model is the best generalizing model, and not just one, and not just the one that performs well on the training data. These are some of the conclusions and the limitations that we came up with. The conclusion: we successfully built and evaluated two models from scratch. That was MobileNet V2 and then EfficientNet V4. We achieved a strong performance despite pre-training. EfficientNet V4 gave us the highest validation percentage of 94 after 10 epochs. And then also MobileNet gave us 92 validation accuracy after 15 epochs. This demonstrated the efficient handling of class imbalance using the OJD class. And the limitations: we're training from scratch, we had limited images, and then we are using CPU to train our models. There was no real influence on mobile deployment tested yet, but we shall do this in future or the next time. That was the conclusion of our model. Thanks for listening, Doctor.